stronger as you go further right. Does that make sense?
Yes.
Okay. So here's, let's say I put two cylinders. One of them is here, starts here. Okay. So now, let's think of, this is a closed surface, right? It's a cylinder. It's like that cup of coffee, but just straight edges, not conic. So it's a closed cylinder. So we can tell in what direction is the normal, is the perpendicular to the area. So on this face, in what direction is the area? To the left, yeah. So the area points this way. That's the normal. How about on this face? To the right. And then how about on the sides? In what direction?
Perpendicular to the surface.
Perpendicular to the surface, away. So it would be like if you're here, it's this way. If you're here, it's this way. So from the sides, there is no contribution to the flux. Because if the field is going horizontal, I mean, it's not going to escape from the sides. It's not going to leak from the, so there is no flux through the sides. Okay? Does everybody get that? That the electric field, if it's going horizontal, none of it will kind of escape through the sides. So there is no flux through the sides. So good. Now let's look at another surface, another cylinder, which is exactly like it, but not exactly like it. It starts here. Here's that other cylinder. It's still subjected to the same field, but it's a little slightly shorter cylinder. Okay? So that's a cylinder subjected to the same field, but slightly.
Say that again.
Okay. So again, in what direction is the area of this face of this cylinder?
To the left.
To the left. Yeah, it's a closed cylinder. And for this one, to the right, and from the sides it's zero, right? So let's think of, since the two cylinders, their right faces, they are at the same spot here, right? At the same spot on the x-axis. At least according to the figure, right? Can you? Yeah, right? I think that's indicated by the figure better than I drew here. So from the right side, the flux is it positive, negative, or zero?
Positive.
It's positive. Why?
Because it's going in the same direction.
Electric field is to the right. The area is to the right. So the angle is 0 degrees, and cosine of 0 is 1. Cosine of 0 is positive 1. So you got positive flux. So from these two faces, you got positive flux. However, from this face and this face, you will get negative flux. Because the area points left, the field points right. Cosine of 180 is minus 1. But which one is most negative? Is it this one? Which one is more negative, this or this?
The bottom one.
The bottom one. And the reason is, well, let's write it. The flux will be either from the left sides, it will be the electric field times the area times the cosine of 180, and that equals to negative EA. But what E should I use here versus here? So the electric field here is stronger than here. It's a larger field here, because as you move to the right, the field is getting stronger. So this number will be larger, but there's a minus sign, right? So it would be, this face would be the most negative.
Got it.
So the answer is C, bottom cylinder, left face. That's where you get the most negative. And the argument is what I argue. Yeah.
So if there's like one more choice where it says top cylinder left face, which one is gonna be more
Can
negative?
you say it again, please?
So for example, if there's like another choice that says top cylinder left face.
There is, yeah, top cylinder left face.
Oh damn.
Yeah, it is negative, top cylinder left face, but not as negative as this one. This one is more negative.
Okay.
Can you repeat that again on why the bottom one is more negative?
Yeah, so the field as you move right is stronger, right? So let's say the field here is, let's say is 1. And as you move right, it gets stronger. Let's say in here, it's let's say 2. And since the two cylinders, they have the same area, right? So let's say for the top cylinder, C from the top, it would be negative 1 times the area, right? But the one at the bottom, it would be negative, but not 1, but 2, because the field now is no longer this number 1, it got stronger, it became, let's say 2, or 1 point something, a little bit more. So it'd be 2 times the area. The area is the same, but this one be more negative, yeah.
Thank you.
Yeah.
So if we were to say, if the problem was saying the electric flux is most positive, then would it be both the top and bottom cylinders to the right would be the same?
Yes.
So
Yes.
it doesn't, so to be positive, it doesn't matter on where your negative starts, technically, or the cylinder starts.
I mean, for this particular problem, yeah, for this particular problem, yeah. I mean, if I take this smaller cylinder and I put it right here, let's say I put it right here, then it would be more negative here, but less positive than this one here, because the field here is stronger than here, right? If I were to put this. Yeah. Oh, what's the, maybe you're going to ask that question.
No, it's a different question. Do they have the same, do they have some rule for if the tube was open? Like what direction would, the normal vector point to?
Let's say it this, I will specify if it's an open
Okay.
surface, yeah. Here is a question. What's the net flux through any of these cylinders?
Positive?
Huh?
0.
Yeah, cause lines in, lines out, 0.
Lines in, lines out,
Oh wait,
Actually,
no, I don't look
positive.
at fields.
but it's stronger.
Yeah.
They're getting stronger.
Oh, yes,
Yeah.
I got it.
So,
Yeah.
is the line the,
It's negative here,
oh, yeah.
but it's more positive here. So it will undo this one and give you some more. So overall, it's actually a positive flux. It's like this. If it's the only way, by the way, or we will get to that actually, I should say. But that was a good intuition, I think Zaid mentioned and others who were inclined to just say 0. If it were, this is rain from outside, the rain goes in, the rain goes out, if there is a hole here, then it would be 0 flux. But this one is slightly different. It's like maybe you have positive charges inside the cylinder itself. That's why there is it gets stronger. Yeah. Well, yeah.
Oh, just to clarify, this is a closed surface, right?
This is a closed surface, yeah. This is a closed surface. Which takes me to the next question. The book asks you this. Suppose you have a box. You have a box, and this is, I know I drew a square, but it's supposed to be a box. Okay? And let's say you don't know anything, right? It's a closed box, you don't know what's in it. But, right, you don't know what's inside the box. You only know that you measure the electric field and then there is some electric field coming out of the box. What can you conclude about what's inside the box? Is it, can you have 0 charge, positive charge, or negative charge?
Positive.
Yeah, you have positive, because you have electric field coming out, electric field goes away from pluses, so there must be some net positive charge. How much is the charge? How is it distributed, and so on? We can figure it out. Good. So, but just by knowing that there is an electric field inside, coming out, I know that there is a plus charge. Similarly, if there is a net electric field into here, right? What can I conclude about the, there must be some net negative charge, right? Again, how much, how is it distributed, and so on, I probably will have to investigate further to figure it out, but not right away. Now Gauss's law takes advantage of what's called of some symmetry. And so here is let's calculate the flux due to a point charge and see what it is. Okay? The flux due to a point charge, and that would be the key. Electric flux U to a point charge. Remember what the definition of the flux is. What's the definition of the flux?
EDA.
Yeah, it's this. E dot dA and integral, right? If I don't know whether it's uniform or whatever, this is the general definition of the flux. So suppose I have a plus charge. Could be a minus charge, but for now, let's say it's a plus charge right there. And I put a box around it, and I would like to figure out what the flux that comes out from this thing. Okay, what is the flux that comes out? So it's inside a box. Okay. Now, what should I do to find the flux out? By definition, the electric flux is E dot dA, right? E dot dA. If it's a closed surface, people use a certain notation if it's a closed surface. And so how do they denote that you're integrating over a closed surface? They put a circle inside the integral, around the integral sign. So if it's a closed surface, they put a sign like this, just to indicate that it's a closed surface. You don't have to put the closed sign, but that's what it means if you see it. You would see it, it's in the book. Does that make sense? The integral sign is just the integral sign. This one is specifically for a closed surface. So let me try to guide you to figure out what the flux is if you're enclosing an electric charge, a point charge. First of all, to put a box, that's probably not the best shape to enclose a point charge. I mean, if you want to enclose a point, what is the most efficient package? How would you package it?
Sphere.
It's a sphere. It would be a spherical thing. Although a box will also enclose it. And the flux coming out of the box or coming out from the sphere will be exactly the same, because it's one charge produces a certain amount of electric field, and you will capture everything as long as you enclose it. So I'm going to use the spherical surface first, and then show you, and then maybe go back and say why the box would have been trouble. So this box will actually be a lot of trouble if you want to do an integral like this. So let me do this. So let's say here's the positive charge, and I would like to know how much flux will come out if I enclose the charge from a surface that completely encloses the charge, right? So here it is. I'm going to draw a sphere. I know this looks like a circle, but it's supposed to be a 3D closed surface. It's a 3D closed surface. It's a sphere. And how much flux comes out? Now, I go back usually to my fire hydrant. If you have a fire hydrant producing 10 gallons per second, if I wrap it by a box, how many gallons per second will go into the box? 10 gallons per second. If I wrap it by a sphere, still, it doesn't matter what the shape is. But to calculate how many gallons per second, not knowing how many they are, it's helpful to use a sphere better, because it is symmetric. It goes with the symmetry. Here is now the argument. So suppose I take a sphere of radius r. Radius r. Okay? Radius r. And it encloses the charge completely. In what direction is the electric field due to a positive charge? Always what? Away from the charge. Yes, the electric field due to a positive charge is always away from it. So let's say if I'm here, the electric field would be this way, right? Electric field. If I'm here, in what direction would the electric field be? That, right? If I'm here, away. If I'm here, away. from here, away. Always away from the positive charge. Now, how much is the electric field due to a positive charge? What's the magnitude?
KQ over R squared?
KQ over R squared, yes. Or if you like, 1 over 4 pi epsilon naught Q over R squared, right? Q over R squared. That's the electric field due to a charge, right? And so, are we good so far? Because this will be important for the argument, for validating the reasoning for Gauss's law. Okay, so that is the electric field. So as long as you're a distance r away from the charge, if you're not moving farther or getting closer, the electric field will have a constant value, right? As long as I'm a distance away, the same distance away, I will get the same electric field. Okay. Again, with the fire hydrant, as long as I'm, let's say, if it's radiating water in every direction, if you're 2 meters away and somebody else is 2 meters away there, you'll get the same amount of water hitting you, as long as you're the same distance away, equidistant. If you move farther, then it's a different story. So we're going to keep the charge at the center of the sphere, and it's a sphere, so that the radius of the sphere is constant, right? So, okay. So that's the electric field strength. As long as I'm a distance r away, it's away from the charge. Now, this is a closed surface. What did we say the direction of the area for a closed surface is?
Away.
Away. Always out, pointing out. So if I look at this little area here, then it points this way. That's the direction of the area. If you're here, the area will point in what direction? That way. Here, it points this way. Here, it points this way. Here, it points this way. So what do you notice about dA and E?
Parallel.
They're always in the same direction, parallel to each other. So let's use this. I got CE, the electric flux will equal to, due to opening charge, will be the integral of E dot dA equals the integral. Now, since E and dA are always parallel to each other, then E dot dA reduces to just E times dA, right? Technically, it's E times dA times the cosine of theta. But theta is how many degrees again?
0.
Yeah, 0. So, in fact, that's right. Why not? E dA and then times the cosine of 0 degrees, right? Of 0 degrees. And cosine of 0 is 1. So that's the, now we get this. E dA, right? E dA. Now, yeah.
And what is orange?
Orange is the direction of the area. That's dA. So the area points out of the sphere, and the electric field also points out of the sphere, and so both are parallel to each other. Yeah.
Why are you doing a circle in the integrals?
That means it's a closed surface. Yeah. It's just a notation to remind us that we're talking about a closed surface, not an open surface.
Okay.
So, are we good up to this point? Now, the next point is this. As long as we're on the surface, so this is the electric field magnitude. Since it's constant, I can pull it out of the integral. It's constant, right? As long as I keep the radius the same, it is constant. So I can pull it out of the integral. So I get this, E times dA, okay? E times dA. So why did I pull out the electric field out of the integral again?
It's constant.
Because it's constant. It doesn't change as long as I keep R the same, yeah.
So for non-uniform fields, would that integral equation still be valid, or if there would be something else we would have to do? Because
For this one?
yeah, for something like that, because there is a picture up there about different like angles and different field magnitudes.
Yeah.
So would the integral still work for that?
The definition of the flux, it still works, yes. You can, the only problem is, can you calculate it or not? It depends how non-uniform is it.
So
So-
in that case, you probably wouldn't take E out, is that?
Oh yeah, if it's not constant, you cannot take it out. But that's the key to Gauss's law. You have to choose a surface by the way, this surface that I drew here, this sphere, it's called the Gaussian surface. And you have to choose your surface carefully so that the electric field will take advantage of symmetry and kind of remain constant. Yeah. And we will do quite a few examples, by the way, on this. Yeah. So I pulled it out again because as long as I'm on the surface of this sphere, the electric field has the same value. Okay? Yeah.
For some reason I'm having difficulty. How can area have a vector?
Yeah. Because it depends on that is the so it's like that's why we started with the simple rectangles or the cup of coffee. The area definitely has the cup has an orientation. So this is the area, and if I can orient it towards you, so it points towards you like that. So there is a vector, definitely a normal associated with this area. Yeah. So.
Yeah.
And it is a tough concept to grasp at first, but there is definitely a normal. Whenever not sure, I always think of my cup of water and rain. And yeah. So I get to here now. Now here's the next key. What is the integral of dA? A. Yeah. Integral of dA is A. And that A will represent the area of the sphere, the surface area of this sphere. So this will give me then E times A. Yeah. So let's write one more. Does anybody remember what the surface area of a sphere is?
4/3 pi r.
That'll be the volume. Yeah, that'll be the volume. Area should be something r squared, right?
4 pi r squared.
It's 4 pi r squared, yeah. That's the area. So let's use orange for the area, 4 pi r squared. And the electric field, what did we say it was?
Q of A.
This one, right? Yeah. So it's 1 over 4 pi epsilon naught Q divided by r squared. Huh?
There's a lot of stuff that cancels out.
Yeah, a lot of stuff that cancels out. There is the 4 pi will cancel out. And then the r squared will also cancel out. And what do we end up with?
Q epsilon naught.
Q over epsilon naught.
That's why we use the one.
Yeah. No. But we will always take advantage of the symmetry. And that's what worksheet 6 is about. We're going to drill this. Okay. So that's the flux. So let's think about what this is telling us. Let's think about what this is telling us. If I enclose a charge, a point charge, the flux through that surface would always be the charge enclosed over epsilon naught. The charge within my surface over epsilon naught. Regardless of where the charge is. Now, here's why I didn't choose a box. Even though you can set up an integral with the box, do a tough integral. At the end, you will end up with Q over epsilon naught. So here's why it doesn't work. I mean, with a box, it would be like just horrible crowding. So imagine, let's say this top face. In what direction is the area on the top face?
Away from it.
Away from it. So the area will point this way, right? Always, from the top face. But the electric field, though, this is the charge. The electric field here, let's say at the edge of the box, it will point this way. And then here, it will point in this direction. In here, it points straight up with the area, but only at that point. Here it changes, and here it changes. And it changes direction and magnitude because you're moving farther. Diagonally, you're farther from the charge than this way. So that would be a terrible integral to do. But if you do it, you will still end up with this. If you don't take advantage of the symmetry. So the bottom line is, Gauss's law will tell us if you enclose only one charge, the flux, this E dot dA will equal to the charge enclosed in that surface over epsilon naught. We'll continue this on Tuesday.